Okay, so I'm going to make an effort to explain why we have this term omega t in so many equations in the A2 syllabus, and hopefully it will put things into context and make it all easy to understand all these different topics. So if you look on the formula sheet, it's kind of like a bit like Where's Wally, okay? So there's all these different things here we have to understand, and here is the symbol omega, okay? And you can see it's V over R, it's 2 pi f. So it's actually radians per second. 2 pi f is the same as 2 pi multiplied by 1 over t, which is the formula for the frequency. So obviously these two equations mean the same thing. So here is a close-up. Now can you spot the two omega t's on the equation sheet? So if you have a look, you will see 2 pi ft, 2 pi f times t, that's the same as omega t, and here it is again, omega t. Once it comes up in oscillation, simple harmonic motion, and another time it comes up with EMF induced in a rotating coil. So you can see both of them for displacements and for EMF. You've got this curve occurring, and we're going to look at why we use that omega t function. So let's unpack omega t a little bit. Okay, so if omega equals 2 pi f, right, which you could also write as 2 pi over t, right, that means that when you multiply it by t, now I'm using capital T for the time period, and little t is the time at present or at the moment you're looking at, right? So if you imagine something that had, say, a frequency of once every 3 seconds, right, or a frequency of a third, its time period would be 3 seconds, okay? So if you were 1.5 seconds into the cycle, right, that would be your little t value. This would be your big T value, and your little t value, that would be 1.5 seconds, right? So then if you was to do what this equation is essentially saying to do, little t over big T, you're going to get the ratio, or like the fraction of how far along in the cycle you are, okay? So in this example it would have been 1.5 over 3, which is halfway through. It's the same as 0.5, okay? You could have been, let's just think another instance of t, it could have been 4.5 seconds. 4.5 seconds would be little t, okay, seconds. So what the hell would that have got us? Well, that would have been, this would have been 4.5, oh, mess, 4.5 over 3, okay, and that would be equal to 1.5. So what this is allowing us to do is to tell you how far along in the cycle you are in whole numbers, essentially. Right, so we'll see how that fits in with the rest, with the other equations we're going to be using with this in a second. Okay, so what are we actually looking at here? We're looking at a nice picture which I found on the internet of a coil rotating in a magnetic field and the associated EMF that would be produced if that was to happen. Now if we pretend that the coil has a normal line through the center of it, that's what we'll call the normal line. If we measure the angle from the normal line to the field lines, at this point the angle would be 0. At this point the angle would be 90 degrees to the field lines. And you can see that when it's at 90 degrees to the field lines you're getting maximum voltage. When it's at 0 degrees you're getting 0 voltage. So if you have your calculator in radians, symbol omega t here, or sorry, our little term omega t there, is going to return, well, if I unpack it again, 2 pi over big T, which is the omega bit multiplied by little t. This is going to return in radians, because 2 pi is one complete cycle. So just to have a look on the bottom of this thing here, 2 pi is one complete wave cycle, one complete rotation, the t over t bit will give you the whole number of cycles you've completed, right? So this bit here, this chunk here, acts to basically, in operation with sine, because sine 0 is what? Sine 0 is 0, right? So when the angle is 0, the voltage is 0. So this whole term here can cancel out everything else in front of it when t and t are the same, right? Or when t and t are a whole number multiple of each other. For instance, if this is 6 and that is 3, then you are 4 pi along, and if you went 4 pi along on the sine curve, you get back to 0. So it just means that we can, for any time we want to specify, we can sub the number into this equation and we can discover where along the cycle you would be. So that's where it's used with EMF. On a side note, the flux linkage, all of that is flux linkage and this is flux, right? But the total amount of flux varies also inside the coils, and it's maximum when the angle is 0 from the field lines, from the normal line, right? So that would be the cos curve. That's why cos is in this equation, right? That's just a side note on the omega t thing. In a minute we'll have a look at the other use of the equation for simple harmonic motion. Okay, so again, very similarly, we've got this, the 2 pi f bits omega and t, and the omega t function essentially allows us to know for any given time where we will be along in terms of radians, where we will be along on either one of these curves. So then you've just got to pick the correct curve. If you know your maximum displacement, let's say from here to here, that maximum displacement in height is 1 meter, right? Then if you start time 0, this is a bit misleading really, but time 0 really would be here. Okay, so at a time a bit later in the future, let's say in 3 seconds, right, where would we be? Well, if you know big T is equal to 3, little t is equal to 3, right? So let's just again unpack this. 2 pi over big T, little t. This chunk will return for you a value of 1. So the whole thing is just going to be 2 pi. So this whole thing is just going to be 2 pi. And cos 2 pi gets us back to 0, right? So at a time 3 seconds, we're back to 0. If we was to do 1.5 seconds, little t is 1.5, right? Not that one anymore. Then this chunk is going to be worth half. It's not, it's going to be, oh yeah, it's going to be a half, sorry, 1.5 over 3. So it's going to be 1 pi, which will be here. So actually that's also 0. And it doesn't matter if you go up to 4.5 seconds, etc. Right? It's still going to give you the correct position along this curve. Okay, so that's how omega t comes up in all these different positions. I hope you found this video useful. If you've got any comments or suggestions, please feel free to make them.